Hello, dear students. Welcome back to the online lecture series of fluid mechanics. I hope you are enjoying my lectures and you are gaining some quite useful knowledge that will be useful for your competitive exams as well as your basic university examinations. So far, we have discussed those properties which characterizes the heaviness of the fluid, namely the mass density, the weight density, and the specific gravity, as well as we have also discussed the properties which originates because of the variation of the density with variation in pressure and temperature. So far we have discussed the properties characterizing heaviness in terms of mainly density. However, in our practical daily life, we may also encounter situations where we will see that two fluids may be of similar densities, such as water and oil, but they behave differently while flowing. For example, it is easier to stir a glass of water than a glass of honey, or even if we try to spill on the floor, the water will flow to a relatively longer distances as compared to oil. Or even in our daily morning breakfast table, you may find that it is quite tough to get our sauce out of the sauce bottle or the ketchup from the ketchup bottle, but it is relatively very easy to pour a glass of water. So apparently there must be some additional property which accounts for the fluidity of a fluid, and that property is what is known as viscosity. So we will discuss this property in detail. So let us see the property which characterizes the fluidity of the fluid. So we will be seeing the property which characterizes fluidity, and which is nothing but viscosity. Now, to determine this additional property, we will consider a hypothetical experiment. In this hypothetical experiment, we will consider two very wide parallel plates that are say that they are separated by a perpendicular distance, say b, and we will consider two cases in which in the first case we will consider that the space in between the two parallel plates is filled with a solid, say steel, and in the second case we will consider the solid is replaced by a fluid. So the situation is something like this. We have two parallel plates, two very wide parallel plates. The same, because we are considering two cases, I am drawing two diagrams. Now see, in the first case, the space in between the two parallel plates, let us say that it is filled with some solid, while in the second case, the space in between the two parallel plates, it is filled with some fluid. Also, we have considered that the perpendicular distance between the two parallel plates, let us say that it is small b. Now also, here in the two parallel plates considered, the upper plate is movable, whereas the below plate, this is stationary. So it will be denoted like this. Here also we will denote the same. So this is stationary plate. This is also stationary plate, and the above plates are movable. These are movable plates. Now what will happen when a force, say F, when a shear force, say F, is applied on the above plate? We will consider that a force, say F, is applied on the above plate. In both the cases we will do the same. First, let us try to see what happens in case of solid. Let us say that at any instant of time, the solid state the solid body, it is represented by, say, this dotted line. Let us say that this is 1 and this is 2. What will happen when the force, a horizontal force F, is applied on the above plate? Obviously, the above plate, it will move like this. And what happens in the solid, this 1, 2, the point 2 will get traversed to a new position, say 2 dash, whereas the point 1 will not get traversed. So we will denote it something like this. So what we find here, that the point 2 is getting traversed to a new position 2 dash. Let us say that this displacement we represented as del A, and the angular deformation which the solid body is undergoing, let this be, say it is del beta. Now when the force F is applied, what happens to the interface between the above plate and the solid body, that is the still body? What happens? It is quite obvious that when a force is applied, the body will try to resist. So there will be a shearing stress that will be developed between the interface. So it can be represented like this. Now this is the interface between the above plate and the solid body. So there is a shearing stress. That shearing stress, let us denote it like this. So we have a shearing stress that is developed, and we will denote it by tau, which is given as F upon A, where F is nothing but the applied shear force and A is the effective area of contact between the plate and the solid body. Now what will happen when the force F is it is retrieved, or when it is removed? Now this point 2 dash will ultimately regain its position, which is 2. 2 dash will again come to 2, provided that the modulus of rigidity is not overcome. So the solid body will try to regain, and ultimately it will regain its original configuration, and it will come to its original position 2. So this is the case of solid. What happens in case of fluids? Let us see the second situation. So in this case, in the case of solid, the angular deformation which we have, that is del beta, which is the shearing strain. So del beta is the shearing strain, and this shearing strain is proportional, directly proportional to the shear stress. This is the case for solids, for elastic solids like steel. What happens in case of fluid? Now see, here also the force F is applied on the above plate F. On the above plate, the force applied, the shear force is applied is F, and as a result of this, what will happen? The above plate will assume a velocity, say it is capital U. Now, when the above plate is moving with the velocity U, what will happen at the contact surface between the above plate and the fluid layer that is in direct contact with the above plate? Remember, here we are assuming that the fluid is made up of different layers from top to bottom. So these are the different layers from top to bottom. We are talking about the topmost contact surface between the topmost layer of the fluid and the above plate. Because of the velocity, because of the force F, what is going to happen here? The above plate, the above layer of fluid, the above most layer of the fluid, it will also assume the same velocity as the above plate U. And this is because mainly of what we call as a no slip condition. And as we move downwards, the layer of the fluid which is in contact with the stationary plate or the bottom plate, it will try to stick, or it will assume a zero velocity. So here at the bottom we have velocity U is equal to 0, whereas in the above, the topmost layer, it is assuming a velocity which is U. So along this perpendicular direction or along the y direction, what we get? We get velocity difference. We get the topmost layer moving with velocity u, and it is decreasing up to u is equal to 0. Now let us also consider what happens between the topmost layer and the layer just below this. What is going to happen here? It is quite obvious that there will be a shear stress that will be developed between the layers. Okay, and because of this there will be some resistance, and because of that resistance the second layer of the fluid, it will move with a velocity lower than the velocity assumed by the topmost layer of the fluid. So we here the velocity will be less than this capital U, and if we move downwards from one layer to another layer, the resistance will go on increasing, and what we will get here, we will get a velocity gradient or a velocity profile like this, whereas wherein the topmost layer is moving with velocity capital U and the bottommost layer is moving with velocity 0. This may be represented by using a velocity triangle representing the velocity profile like this. So it is because of this shear force that a shear stress is getting developed, and it is because of this shear stress that what we are getting here is a velocity gradient. Remember this term, velocity gradient. Velocity gradient. So what is the cause of this velocity gradient? The cause of this velocity gradient is nothing but the shear stress. This velocity gradient may be represented as the change in velocity du upon dy, as we have taken this, as we generally take this direction as y-axis and this direction as x-axis. So the velocity is changing along the y direction. So here we are indicating that the velocity gradient is the change in velocity along the y direction. So we can say that the shear stress tau, which is equal to F upon A, this is directly proportional to du upon dy. Now this is a very important equation, and this equation is generally known as what we call the Newton's law of viscosity. Now we will also try to deduce another expression in terms of deformation, as we have obtained here that the shear strain is directly proportional to shear stress, or in other terms we can say that the shear stress causes a shear strain and both are directly proportional to each other. To understand that, let us assume that this is a fluid element at some time, say t0. So I am trying to draw it here. So here this rectangle, rather this square, this represents a fluid element, say 1, 2, 3, 4, and this is at time t is equal to 0. Now here, as we have already seen, that the topmost layer is moving with a velocity greater than the bottommost layer. So let us say that if the bottommost layer, that is which is 1, 2, it is moving with velocity du, or yes, if it is moving with velocity du, or let us say that it is moving with velocity u, small u, then we can say that the topmost layer, the top layer of this fluid element will move with more velocity. Let us say that it is u plus du. Now this is the case when t is equal to 0. After some time, this fluid element is going to deform, and now again let us try to draw it here. So we have this deformed fluid element. Here we'll try to superimpose the initial fluid element by the dotted lines. So here we have 1, 2, 3, 4, which is our initial fluid element, and the rhombus, which is in blue, this represents the fluid element which have undergone deformation, and this is, let us say that this is at time t. Now, as you can see that let us try to represent it. One is the same, point 1 is the same, point 2 is the same, but this 3 has traversed to another position 3 dash, and the 4 has traversed to another position 4 dash, and this deformation, the angular deformation, let us represent it as del beta. Okay, so now let us try to see what distance they are going to travel, or in order to find out the deformation, let us try to find out 3 dash, because you know that tan d beta, tan del beta, this will be calculated as 3 dash upon 3 2, where 3 2 is what we can say that this is dy, because we have taken this direction as the y-axis. So how to find out this value 3 dash? Now when the point 2 is moving with velocity u and it has reached to this position at time t, so the distance traveled, this will be u into, let us say that the time elapsed. So let us say that this is at time say t, and here the situation is at time t plus del t for convenience. So if this is moving with velocity u, the distance that will be traveled between the points 2 and this 2, this will be u. Let us say that this is dt. So this will be u dt. Similarly, you can also find out the distance 3 dash, and this will be equal to u plus du into dt. Now 2 is u dt, and 3 dash is u plus du into dt. So 3 dash can be calculated as u plus du into dt minus u dt upon this 2 we have dy. So on calculating this, what we will get, u dt plus du dt minus u dt, and so here we will get du dt upon dy. Now I am rewriting this here because of space constraints. So what we have here, we have tan d beta, it is equal to, here also I will take d beta only because we are considering d elsewhere. So tan d beta can now be written as du dt upon dy. Now if this d beta is very small, this tan d beta can be approximately written as d beta, and so we have d beta is equal to du dt upon dy, and on rearranging, what we get here, we get d beta upon dt is equal to du upon dy. So this is a very important result which we have got. What we have got here, we have got that the velocity gradient velocity gradient is equivalent to, now what is this? E beta is the angular deformation, and here we have dt, which is time. So we can say that this is the rate of angular deformation, or you can also say it the rate of shear strain, or simply we can say it as shear strain rate. So what we have got here in case of fluids, the shear stress tau, it is directly proportional to du upon dy, and this du upon dy is equivalent to the rate of angular deformation. So whereas in case of solids, what we have got, that the shear stress was directly proportional to shear strain. This was the case of solids. Whereas in case of fluid, what we get? In case of fluid, we get a different result, that the shear stress, it is directly proportional to the rate of shear strain. Now this is a very important result because it also indicates that the fluid is continuously deforming, or there is a continuous change in the rate of deformation. So we have got a very important expression, a very important equation, which is called the Newton's law of viscosity. So let us try to see this Newton's law of viscosity. What this Newton's law of viscosity says: Newton's law of viscosity is the result which we have received, which we have obtained so far. It says that in case of fluids, we have the shear stress, or Newton's law of viscosity, states that the shear stress, it is directly proportional to the velocity gradient or it is directly proportional to the rate of angular deformation or the rate of shear strain so we have tau directly proportional to du upon dy or tau, it is directly proportional to d beta upon dt. Now the fluids which follows the Newton's law of viscosity, they are termed as Newtonian fluids, and most commonly used fluids such as water, oil, these all are comes under this category of Newtonian fluids. And in this case, what will happen in case of water or the most commonly used fluids, the shear stress will be directly proportional to the shear strain rate. So we know that the unit of tau, it is Newton per meter square. Now, in order to remove this proportionality constant, we will use a constant of proportionality. So we have tau, it is equal to mu du upon dy, where this constant, this is a proportionality constant, and this is known as coefficient of dynamic viscosity, or it is also called the coefficient of absolute viscosity, and we can obtain the value of mu as tau upon du by dy. Now let us try to find out what will be the SI unit of mu. We know that for tau we have Newton per meter square, and for du upon dy we have for velocity we have meter per second, and for dy is the distance, so here we will get divided by meter, or we can rewrite this as 1 upon meter. So meter gets cancelled out and we get Newton second per meter square. Or even this Newton per meter square is also known as Pascal. So we can write down this as Pascal second. So this is the SI unit of dynamic viscosity, or the coefficient of dynamic viscosity. But remember, one most commonly used unit for dynamic viscosity is not Newton second per meter square or Pascal second. It is known as poise. So it is actually in the absolute metric system, and it is known as poise, and 1 poise is equal to 0.1 Pascal second. So see, we have 1 poise which is equal to 0.1 Newton second per meter square, or 0.1 Pascal second, or we can say that 1 Newton second per meter square is equal to 10 poise. And even this is also a very you can say this is a very large unit, so sometimes we also use a smaller unit which is called centipoise, and that centipoise may be defined as it is nothing but the 100 times the poise. So 100 times of the poise is what we call as centipoise, and the viscosity of water, the value of viscosity of water is equal to 10 raised to the power minus 3 Pascal second, or 10 raised to the power minus 2 poise. You remember this? For water, in terms of poise, we have the viscosity of water at 20 degrees Celsius. It is equal to 10 raised to the power minus 2 poise. For water at 20 degrees Celsius, it is 10 raised to the power minus 2 poise, or in terms of SI unit, we will say that it is equal to 10 raised to the power minus 3 Pascal second. Now here again I have mentioned here that the viscosity of water, this is the value of mu of water at 20 degrees Celsius. Again I am mentioning here the temperature because, as I have discussed earlier, the properties are functions of temperature and pressure, and they varies with temperature and pressure. We will see in the next lecture how this viscosity is going to vary with changes in temperature and pressure. Also we will see some significance of viscosity, or we will also try to characterize viscosity. We will see the two categories of fluids which are defined on the basis of this Newton's law of viscosity. There are some fluids which are called Newtonian fluids, while there is another category which we call as the non-Newtonian fluids. So that's all for today. Thank you so much.